Welcome to this next video in the playlist on ring theory. In this video, what we're going to talk about is adjoining elements onto a ring. Okay, now this is a difficult topic and it leads on to so much, so it's the foundations of so much, so it's a really important topic as well. So what I want to spend quite a long time doing is motivating what we're actually trying to do. Okay, so firstly, then let's begin with this motivation. Okay, so some motivating examples for what we're trying to do here. Okay, so some classical examples are, we know about this ring number system, which is the rationals under addition and multiplication. Now, of course, the rationals actually forms a field, but all fields are rings, so the rationals is certainly a ring with addition and multiplication defined on it in the normal way. Now, the rational number system has no solution to the equation x squared minus 2 is equal to 0. Okay, there is no rational number that you can put in place of x here and have it satisfy that equation. Okay, there is no square root of 2, we can say, in the rational numbers. No rational number squares to give 2. Okay, so a classical example of the problem of adjoining elements onto a ring is, can we add in a new symbol into this number system here which will square to give 2? Can we put in a solution to this equation formally and create a bigger ring which then does contain this ring and also has a solution to x squared minus 2 is equal to 0? Another classical example relates to the real numbers. Now again, the real numbers is a field with addition and multiplication defined on it, but again, all fields are rings, so it's an example of a ring. Now, the classical example of an equation that can't be solved in the real numbers, that has no solutions, is x squared, plus 1 is equal to 0. Okay, there is no real number which will satisfy that equation. No real number squares to give a negative 1. Okay, and of course, again, we want to ask the question, can we extend the real numbers? And I'm sure you'll know the answer to that. Can we extend the real numbers to some larger ring or potentially field which will contain the entire real numbers but will also have a solution to this equation? So those are the two absolutely classical examples of what we're actually trying to achieve with adjoining elements to a ring. Can we formally add in some more symbols and have a new symbol which is going to satisfy these algebraic relations which currently have no solution in the algebraic system as it stands? Okay, now, to actually give an example of this, I am not going to use either of these two, and the reason is that these two are, although they're classical number systems, so you have good intuition for them from classical algebra, they are actually incredibly complicated. I mean, the real numbers, in real analysis, people spend about 3 weeks going over the construction of the real numbers, the rigorous construction of the real numbers. It's incredibly complicated. Okay, these are really complicated number systems. So to actually give you an example of adjoining an element to a ring, which is what I want to begin with, a motivating example, so it won't be a formal example, it's going to be a motivating example to really nail in your head exactly what we're trying to do here before we go on to the formalization of all of this. I want to give you an example in terms of a really simple ring. And I want the simplest ring that has a non-trivial example. Now, the simplest ring, of course, of them all is the 0 ring. That you can't really do this for, okay? So we're not even going to touch the 0 ring. It's too trivial. But then we'll go a step up from that. So from a ring that just contains one element to a ring that contains 2 elements. And this ring actually is a field, and it's the prime field F2. So we're going to look at an example with F2, and the reason we're going to use this example is, although it's less intuitive than these two, you haven't been using it for years and years and years the way you have been using these two. It is finite. It has only 2 elements. You can write the entire thing out on a piece of paper right in front of your face, and that is why we're going to use it to get an understanding of this very complicated topic of adjoining elements to a ring. Okay, so whenever in abstract algebra you've got some complicated thing to get used to, I would always advise you to go to finite examples that you can write out completely on a piece of paper. Okay, although these are of course extremely important, and often the concepts are more important when applied to these. After all, this is why we're developing all of this, so that we can gain understanding of these classical number systems that physicists and engineers and other applied mathematicians use all the time. So although those ones are potentially more important, these ones you can put on a piece of paper, and that makes them fantastic as far as intuition is concerned. So we're going to do that here now. So first of all, let me just remind you of the prime field F2. Okay, so it's a field, which of course is a ring, and it's a field that contains just two elements, and we'll call these two elements 0 and 1. The additive identity and the multiplicative identity respectively. Okay, now I don't just want to stop there, I want to write out the addition and multiplication laws in front of you now, so let's do that. So let's firstly have our addition law here. So the addition law on this field F2 then, so I'll give both elements a row in this addition composition table, and I'll give both elements a column in this addition composition table, and I think I'll colour it in here in pink, like so. Okay, and how then is the addition law defined? Well, there's only one way it can be defined, because there's only one group of size 2. So 0 will have to add to everything to give 0 back again, so you'll have 0 here, sorry, not 0 back again, the other thing back again. So 0 will add to anything to give the other thing back again. So it's the additive identity, so it'll send 1 onto 1, 1 plus 0 will be 1 as well, and then 1 plus 1, you're forced to make this 0, because remember, for this to be a group, all of the rows and all of the columns must contain each element of the group once and only once. Okay, so if you look at this row here, you can't put 1 there, so there's only one other option that you can have there, which is 0. So there's our addition law, and of course that's just the cyclic group on two elements, and it is indeed an abelian group. Okay, so it satisfies the axioms that we need it to satisfy to be the addition law for a ring here. And then we'll have the multiplication law, and I've just realised that I haven't left myself as much space as I wanted. I'll have to extend this later on. Well, we'll have to redraw it out for later on. I was hoping to draw this over here, but I've ruined it now, so never mind. So here is the multiplication law then. Okay, so again I'll give both elements of this algebraic system here a row, and both elements of the field a column here. And then how does multiplication work on this? Well, of course we know that the additive identity must multiply by everything to give the additive identity back again, and 1 is the multiplicative identity, so it must multiply by everything to give itself back again, the other thing back again, and the only thing that's not trivial here is 1 times 1, and that will have to give 1 here. Okay, so there are the addition and multiplication laws on my finite field F2 here. Okay, so what equation then can I come up with that doesn't have a solution in here, for which I want to formally adjoin a solution onto this number system? Okay, so the equation that I can concoct that has no solution in this field F2 is the equation x squared plus x plus 1 is equal to 0. Okay, I claim that there is absolutely no solution to that in this structure, and it's very easy to see why that is. We can do this just by brute force, because we have only two elements, and that's why this is lovely, that if all else fails, you can do things by brute force. Okay, so let's just put in both elements that we have here and see that neither of them satisfies this equation. So 0. So if we put 0 in here, we'll do 0 squared. 0 times 0 is still 0, so that's 0. And then we're adding it onto 0. 0 plus 0 is still 0. Okay, and then we're adding 1 onto that. 0 plus 1 is 1. So the answer here would be 1, not 0. So 0 does not satisfy this equation. Now let's try the other element of this field here, which is 1. So if we put in 1 here, we'll have 1 squared. 1 squared is 1, so we'll get 1 there. then we'll add on another 1. 1 plus 1 is 0, so we'll get 0 here, and then we're adding on 1 to 0, so again we'll get 1. So 1 does not satisfy that polynomial equation either. Okay, so there is no element in this field that satisfies that equation. So what I now want to do then is formally add on a solution to that equation. And by the way, the reason I had to pick a more complicated equation than these is you'll see that the only two equations that I could concoct of this form, where there's no degree 1 term in the quadratic, are x squared is equal to 0 and x squared is equal to 1. Those are the only two quadratics of this form that I could concoct, okay? And of course there's solutions to both of those. So x is equal to 0 is a solution for this one, and x is equal to 1 is a solution for this one. Okay, so it wouldn't be a good example to pick. You could use it, but we're not going to, well, we will see that you could use it later on, but we'll use this one instead. We'll use one that doesn't have a solution at all, so that we stick with our normal motivation for actually doing this. Okay, so what I want to do then is I want to just stick in another symbol into this number system that is going to satisfy this equation. So I want to extend this number system, put more stuff into this number system so that I now do have an element that actually satisfies that equation. Okay, and of course the new number system that I'm going to get, the ring extension if you like, it is going to have to contain all of the original ring, otherwise this equation would no longer make sense. Well, because it's only involving 1 and 0, I suppose it would make sense because they have a meaning in all other rings. But normally, if this contained elements other than 1 and 0, you would have to have the original ring contained in there for the polynomial to still make sense. Okay, so what I'm going to do then is I'm just going to create a new symbol, stick it into here, and try and define the structure so that it will obey the axioms of ring theory, and so that it will now have a solution to this equation. Okay, so the first fun bit is that I get to create a symbol which is going to be my solution to this equation. So I get to pick my favourite tacky Greek symbol, and my favourite tacky Greek symbol is the Greek symbol zeta, so we'll have zeta. So I'm going to stick in an extra symbol into this set. So this bit's going now, and we've now got an extra symbol in there. Okay, so I'm going to stick in another symbol into this set, and I am going to try and make zeta the solution to this equation. Okay, so I want zeta squared, so I'll write this out. I want zeta squared plus zeta plus 1 to equal 0. Okay, right. So, what I now need to try and do then is add zeta in to the addition and multiplication tables here. Now, I have probably just left enough space to do this for the time being, so we'll use these ones here for now. Okay, so I'm going to give zeta a column here. I'm also going to give zeta a row here. Okay, and of course I'll do the same in my multiplication table, like so. Okay, so zeta's got a row and zeta's got a column. Okay, so let's try and actually work out what the entries are going to be. Now you might wonder, well, how on earth are you going to do this? Well, we want this new structure that we are creating to still obey the axioms of ring theory, and that is going to help us a huge amount here. Okay, so remember, 0 is still going to be the additive identity, so we can instantly say what this entry is going to have to be. It's going to have to be zeta, and we can instantly say what this entry is going to have to be. It's going to have to be zeta as well. Okay, so far so good. We've worked out 2 entries in the addition table. We can also work out a few entries in the multiplication table. 0 has to multiply by anything to give 0 back again, so we can work those ones out as well. In addition, some more easy ones in the multiplication table here. What's 1 times zeta going to equal? Well, of course, that's just going to be zeta, because 1 is the multiplicative identity. We wanted it to remain the multiplicative identity, so zeta, 1 times zeta had better be zeta. And again, zeta times 1 had better be zeta. Okay, now coming back to the addition table over here, this is where we run into problems. Okay, and this is where unfortunately we realise that we can't do this. We're going to have to stick in another symbol as well. We can't get away with just sticking one symbol in. Okay, and it comes when we, for instance, ask, what should I put here? What should zeta plus 1 be? Well, I initially would have liked to just have 3 symbols. I didn't want to have to add in another symbol. I mean, my imagination's getting a bit tired. I don't want to have to come up with another symbol. Okay, so I'd like to try and just keep it as 3 symbols, but what should zeta plus 1 be? Okay, it can only be one of these things, 0, 1, or zeta, but the problem is it can't be any of them, and the reason is I want this addition table to be an abelian group, otherwise the thing that I'm building here isn't going to be a ring. So we know that in group composition tables, each row and each column, and I pointed at those in the wrong order, each row and each column has to contain every element of the group once and only once. Okay, so if we, for instance, look at this column here, that tells us exactly what the entry here has to be. It has to be zeta, because the other 2 elements of the ring have already been used up, so this one will have to be zeta. But look, that ruins this row now, because I've got zeta twice, so I'm stuffed, basically, that I cannot define that and make this a group. It won't work because I can't make it so that the rows and the columns each contain the elements of the ring once and only once. So I have a problem. I cannot put any of the symbols that I've already got into this socket, so I'm going to have to create another symbol. There's no other choice. I have to create another symbol without changing what I've already got, and I don't want to change what I've already got, otherwise the equation starts to mean a different thing. Remember, I want the original number system to be completely contained in my new bigger number system. I want it to be an extension of the old one, so you are not allowed to start changing what you've already got. Okay, so I'm going to just have to stick in another symbol. Now, I don't want this to get too complicated, so I don't want to create a brand new symbol. Instead, I'm just going to denote the answer that we're going to put in here as 1 plus zeta. Okay, so I'm going to use this as my symbol. 1 plus zeta is going to become my symbol. And this is a very convenient symbol to use because it will remind us of the fact that if you add zeta to 1, and of course because we want this to be commutative, the other way around, 1 to zeta, you will get 1 plus zeta. So it's a very nice thing to actually use as the symbol here. Okay, so what we're now going to try and create then, this new field. At the moment we've now got, or this new ring, it is actually going to be a field, but at the moment we're just trying to make it a ring. So this new thing that we're creating here, we're now up to 4 symbols. So we've got 0, 1, zeta, and zeta plus 1, or I'd rather denote it 1 plus zeta. Okay, so these are my 4 symbols so far, and what I want to now do is actually show you that with 4 symbols you can make this work. Okay, with these 4 symbols we can actually produce a ring extension of our original field F2 here. Okay, so this is why I didn't leave enough space, so we are going to have to redraw out the addition and multiplication tables, I'm afraid. So here is my new addition table, and here is my new multiplication table here. Now, I need to put every single one of the elements in my new ring to be, my ring extension to be, I need to put every single one in a title for a row and every single one in a title for a column, so I'll get on with that. 0, 1, zeta, and 1 plus zeta, and then we'll have it up here as well, 0, 1, zeta, and 1 plus zeta here. Okay, so we'll now denote this in purple here, like so, and multiplication, again, we'll have all of them given a row here, so 0, 1, zeta, and 1 plus zeta, and all of them given a column, 0, 1, zeta, and 1 plus zeta here, and again, I will colour that in purple here. Okay, right, so now let's try and actually work out the entries in these 2 composition tables here. So firstly, let's fill in the bits that cannot change, the bits from the original field F2. So 0 plus 0 is 0, 0 plus 1 is 1, 1 plus 0 is 1, and 1 plus 1 is 0, and multiplication 0 times 0 is 0, 1 times 0 is 0, 0 times 1 is 0, and 1 times 1 is 1. Okay, now let's fill in the bits that have do, or at least are obvious, and in fact a lot of this it's now set exactly. In fact, all of this, it's set exactly what it has to be. There's only one way that we can define this, okay, as we'll see. But let's do the obvious bits first. So 0, we want that to remain the additive identity, so that's going to have to add to everything to give the other thing back again. So 0 plus zeta will be zeta, 0 plus 1 plus zeta will be 1 plus zeta back again, zeta plus 0 will be zeta, 1 plus zeta plus 0 will be 1 plus zeta. Okay, now of course we created 1 plus zeta so that it would be the answer to zeta plus 1, so the answer to zeta plus 1 will be 1 plus zeta, and of course the answer to 1 plus zeta will be 1 plus zeta. Okay, so that's all of the easy bits that we've already done for the addition table. Now let's do the easy bits for the multiplication table before doing the less easy bits. Okay, so 0 must multiply by everything to give 0, so those are easy. 1 must multiply by everything to give the other thing back again, so 1 times zeta must be zeta, 1 times 1 plus zeta must be 1 plus zeta, zeta times 1 must be zeta, 1 plus zeta times 1 must be 1 plus zeta. Okay, so only 4 entries that we have to do for multiplication, so it's not looking too difficult. Now, how do we work out what the other entries must be? Well, you have to remember, we want this to obey the axioms of a ring. Okay, so we are just going to use the axioms that we want it to obey to work out what the other entries in these composition tables must have to be if we want it to have any chance in the world of obeying those axioms. Okay, and I want to stress that doing what we're about to do doesn't prove that the thing that we'll end up with will obey the axioms of a ring. It's just that if we don't do it in this way, it doesn't stand a chance of obeying the axioms of a ring. Okay, so let's work this out then. So 1 plus 1 plus zeta, that's probably a nice place to start. So we're now considering what is 1 plus the symbol 1 plus zeta. Well, this is the point that we remember that 1 plus zeta, this symbol, is actually equal to 1 plus zeta, where this is the real composition. Okay, so we can actually think of this as 1 plus and then 1 plus zeta here. Okay, where all of these are compositions, so I might just colour them in. So we've gone from thinking about this just as a symbol to actually thinking of it as 1 plus zeta in the composition law that we've got here. Now, we want the composition of addition here to obey associativity, so we better design this so that this is the same as 1 plus 1 plus zeta, like so. Otherwise, if we don't have it like this, this thing doesn't stand a chance of obeying associativity. Okay, so what is 1 plus 1? Well, that's 0, so we'll end up with 0 plus zeta, and of course 0 plus zeta is just zeta, so now we know the answer there must be zeta, and of course, because we want the addition to be commutative, I can instantly say that 1 plus zeta plus 1, the other way round, also has to be equal to zeta. Okay, so this is what I mean by using the axioms that we want it to obey and saying, okay, if we want this structure to obey these axioms, then this must be true. Okay, if this isn't true, then it doesn't stand a chance of obeying those axioms. Okay, right, let's do it again. So zeta plus zeta then, the next one, this entry here, zeta plus zeta. How are we going to do that? Well, remember, we want this to be a ring. So we want distributivity to be true, so we could factor out zeta here. Okay, we could view each of these as 1 times zeta plus 1 times zeta, and then factor out the zeta, so this becomes 1 plus 1 times zeta. But of course 1 plus 1 is 0, and 0 times zeta is 0, so the answer here is going to be 0. So zeta plus zeta has to equal 0. Okay, again, we're just using the axioms we want it to obey and then working it out from that. Okay, if that isn't true, then it doesn't stand a chance of being a ring. So this one's set as well if we want it to be a ring. Okay, then let's do zeta plus 1 plus zeta. So we're now considering this one here, zeta plus the element 1 plus zeta. And again, we will use the fact that we want addition to obey associativity and commutativity. But firstly, we'll have to use the fact that 1 plus zeta really is 1 plus zeta. Okay, so we now view this as all additions, whereas firstly this was just an addition and this was just a symbol. Okay, but now we've viewed this as actually being 1 plus zeta. Then what we can do is apply associativity and commutativity of addition to meddle around with this a bit, and we'll easily see that this is equal to 1 plus zeta plus zeta. Okay, so if associativity and commutativity are going to work, you can easily do that. Okay, so you can reassociate to get the brackets around those, commute them around if commutativity is going to be true, and then reassociate to have the brackets around zeta plus zeta again. Okay, so if we want addition to obey the axioms of a ring, it better be the case that this is true. Okay, zeta plus zeta, of course, is going to equal 0. We've just done that one. So we now have 1 plus 0, which of course is just 1. So the answer there is 1, and then again, if we want it to be commutative, the answer here will be 1. And then we've only got one more to work out for addition here. So we want to work out what is 1 plus zeta plus 1 plus zeta. Well, again, the first move is just to say, initially, this was the only addition here, but of course we now turn these from being the symbols to actually being the additions here, and then with a little bit of help from associativity and commutativity, we can say that this has to be the same as 1 plus 1 plus zeta plus zeta. Okay, like so, where all of these are additions in our actual ring. And of course, 1 plus 1 is equal to 0, zeta plus zeta is equal to 0, so the entire thing is going to be at 0 there. Okay, and those of you who are well up on your group theory will recognise that that addition law that we've created here is actually the Klein 4 group. There are only two groups of order 4, the Klein 4 group and the cyclic group of 4 elements, and that's certainly not the cyclic group of 4 elements, so it must be the Klein 4 group. Okay, right, so now let's work out the entries that we have to have here for multiplication to work and obey the axioms of ring theory. Okay, so firstly, let's and we have to use the fact, one other fact we're going to use here as well. We want it to obey this equation. Remember, we were creating zeta so that it was true that zeta squared plus zeta plus 1 is equal to 0. So we want this equation to be true. Okay, now we can rewrite this equation now a little bit. We now have our addition law all defined here in our ring extension to B. Okay, so we can work with this a little bit. So what I can do is add zeta and 1 onto both sides here. So imagine adding zeta and 1 onto both sides. And you might think, well, why on earth are you doing that? Well, the reason is that zeta will add to zeta to give 0, and 1 will add to 1 to give 0. So this actually becomes zeta squared is equal to zeta plus 1. So I've nicely rearranged that, okay, because of the fact that zeta and 1 are their own additive inverses, basically. So zeta is its own additive inverse, and 1 is its own additive inverse. In fact, everything is its own additive inverse in this Klein 4 group that we've created here. Okay, so in fact that tells me instantly what zeta squared has to be equal to. If it's going to obey this equation, zeta squared has to be equal to 1 plus zeta there. Okay, so zeta squared had better be equal to 1 plus zeta. Now let's work out what zeta times 1 plus zeta is going to be equal to. Well, here again, the first thing we're going to do is remember that 1 plus zeta actually really is 1 plus zeta. Okay, so we go from thinking about that plus just as being a symbol to thinking of it as being the addition over here. And then because we want multiplication to distribute over addition, we can split this into zeta, which is zeta times 1, plus zeta squared here. But zeta squared is 1 plus zeta, so this will become zeta plus 1. Okay, and then we can apply associativity here to say that this is zeta plus 1. Zeta plus zeta is 0, so this is actually going to end up being 1. And the same is going to be true here because we want multiplication to obey commutativity. Okay, or at least, well, we might as well try for it to obey commutativity. Okay, you can work out the other way around. You can work out that 1 plus zeta times zeta is also going to be this. Okay, so I'm just trying to justify why that one would be 1. We're not going to insist that this has to be commutative. It doesn't need to be commutative in order to be a ring, but if you do work out what 1 plus zeta times zeta is, following the exact same argument as this, you'll get that it also has to be equal to 1. Okay, so it's forced upon us. That isn't a choice. That is something that's forced upon us. Okay, right, so now let's do 1 plus zeta times 1 plus zeta, the final one here. And again, of course, the first thing we'll do is stop thinking of these just as symbols and start thinking of them as 1 plus zeta and 1 plus zeta there. Then we'll apply distributivity, which we want to be true in our new structure that we're creating, and we'll get that this is 1 plus zeta plus, so that's this one times this one times this one, and then plus zeta, so zeta times 1, and then plus zeta squared, okay? So just applying distributivity there, and now what we'll do is firstly we'll add zeta to zeta here. Now when we add zeta and zeta together we get 0, so that goes. So that middle bit's gone now, and then we'll apply the fact that zeta squared is equal to zeta plus 1 if we want this equation to be true up here, okay? And then we can apply associativity and commutativity of addition, move the 1's around, get them to cancel with each other to give 0 here. So the answer overall here will just be zeta, and therefore that's the answer that we're going to have there. Okay, so everything is forced upon us, okay? If we want the axioms of ring theory to actually hold true for these two composition laws, we don't have any choice of what the entries in here are actually going to be. And I want to stress, I have not now proven that this actually is a ring. Okay, you could now go through and prove that this is a ring. In fact, it's better than a ring, it's actually a field, okay? But I haven't proven that. I've just said, if we want it to be a ring, this has to be true because we want it to obey these axioms. But I haven't actually proven that the structure that I did end up with was actually a ring. It was just the case that if you didn't define it in this way, it had no chance at all of being a ring. Okay, so this was the only way I could possibly have defined this to even have a hope of it being a ring. Okay, but if you do actually check the axioms of ring theory, you can go through this and check that it obeys the axioms of ring theory, and as I say, it even obeys the axioms of field theory. Okay, so I have now taken this small field here, the prime field F2, and I have extended it up to this larger field. It is a field here, but first and foremostly, these are both rings, and I've extended this ring to a larger ring here. Okay, and I claim that this ring here now actually has a solution to the original problem that the original field or ring didn't actually have a solution to. So this equation x squared plus x plus 1 is equal to 0. Let's just check that zeta here actually does satisfy this. Okay, so if I put in zeta, if I consider what is zeta squared plus zeta plus 1, so zeta squared is 1 plus zeta. Okay, if I then add 1 plus zeta to another zeta, so we'll do 1 plus zeta to zeta, that will give me 1, so that's the x squared plus x bit done, so I've got 1 here, and then I'm adding 1 to 1 and I'll get 0. So zeta does indeed actually obey this equation, it satisfies this equation. Okay, so there is an example of actually extending a original ring that you have to a bigger ring, which we call a ring extension, which contains the original one and now has a solution to this algebraic problem that previously our number system didn't have any solutions to. Okay, so there is our motivating example. Now I realise this isn't rigorous as of yet, okay, this looks awful, okay. Firstly, we still have a huge amount of work to actually prove that this obeys the axioms of a field, and you're thinking most likely, but what about these cases up here, the rationals and the reals? It's going to be a huge amount of work to do this for those. For every single time we want to do this, you'll have to do all of this work, you'll have to then go through and check that it actually obeys the axioms of a ring, what you end up with. Okay, so it looks like a nightmare at the moment. What I will do in the next video is I will formalize this. I will show you an incredible way of doing this really simply. And the brilliance of this way of doing it is that you don't need to worry about the thing that you end up with being a ring. The difficult bit is the conceptual bit of understanding why this formal way of doing it actually captures exactly what we intuitively want to do. So I hope this is an intuitive introduction to the concept of adjoining elements to a ring, and we'll go through the formal concept in the next video.